Continuing our series with hyperbolics, we are now going to introduce calculus on the hyperbolic functions. We will be using hyperbolic functions in more advanced calculus in the future, but for now this is just very much an introduction to differentiation and integration on some very basic hyperbolic functions. So let's just start from first principles. So let's start with y equals sine of x. What I'm going to do is I'm going to write this in exponential form. So we know that sine of x is e to the x minus e to the minus x, all divided by 2. And I'm doing that because I know already how to differentiate the exponential functions from A-level maths. So e to the x differentiates to e to the x, and then e to the minus x differentiates to minus e to the minus x, but of course that's minus, so that becomes a plus. And the 2 is just a constant, that just stays as it is. Oops. So that's what it differentiates to under the differential operation. And then we recognise that this is the exponential definition of the cosh function. Okay, so sine, the trigonometric function, differentiates to cosine. And in hyperbolic functions, the sine function differentiates to the cosh function. Okay. This then, of course, means that the integral of the cosh function dx is going to be the sine function plus c. Okay, so if sine differentiates to cosh, then cosh integrates to sine. Okay, we can do the same thing with the cosh curve. So the cosh function we know is e to the x plus e to the minus x, all divided by 2. And then if we differentiate that with respect to x, we'll end up again with e to the x minus e to the minus x, all divided by 2, which we recognise as the sine function. And here we get our first difference with against the trigonometric functions. Cos, the cosine function, differentiates to minus sine, but cosh, the hyperbolic function, differentiates to positive sine. Okay, so just be really careful when you are applying differentiation to hyperbolics. This then, in turn, means that the integral of sine with respect to x is the cosh function. Again, plus c. Okay, so cosh differentiates to sine, therefore sine integrates to cosh. Okay, so there's no sign change with these as you would get with trigonometric functions. And then the other base hyperbolic function is the tan function. So we recognise that this is sine of x over cosh of x, and we could write this as exponential functions and then go from there, but we now know how to differentiate sine and cosh, so I'm going to use the quotient rule on this. So the top is going to be sine, so u is sine, u primed then is the cosine, v is the denominator, which is cosh, and then v primed is therefore sine. Okay, positive. And now we can plug that into the differentiation quotient rule formula. So dy by dx therefore is going to be equal to vu dash, so that's going to be cosh squared of x, minus minus u v dashed, so that's sine squared of x, and then that's all divided by v squared, which is cosh squared of x. And we recognise that the top is actually the number 1. It's the equivalent of the Pythagorean identity. Look back at previous videos for that. So that is just 1 over the cosh squared of x, which we could write as the sec squared of x, which again looks familiar because tan differentiates to sec squared, and we have here tan differentiates to sec squared. Okay. All right. So those are the base ones. So that's what we're going to be looking at in these videos, or in this video. Okay. So I've got 3 examples. Bearing in mind, you need to kind of have in your head everything you've done in differentiation and integration up until this point. This is an addition to everything you've already learned. Okay, So let's find the exact coordinates. So we're looking for maybe some logs or e's or roots in our answer. Exact coordinates of the stationary points of this curve here, and determine its nature. Actually, that should only be one. There's only one stationary point of this curve. And then we're going to sketch the graph. Okay, so you need to know from regular maths that if you're going to find a stationary point on a curve, you need to set the derivative to 0. Okay, that's exactly what stationary point means algebraically. Whenever you see that, you should immediately be thinking dy by dx, the first derivative, is 0. Okay, that should be that's what that means. So let's differentiate this. We're going to end up with dy by dx is equal to, and in the same way that you would differentiate cos of something times x, you would multiply by it, the constant in there, and by the chain rule. We're going to do the same thing with cosh. So it gets times by the fifth. So it's going to be 3/5 times the sine of x on 5. And again, the contents of the hyperbolic functions won't change. So x on 5 stays x on 5. And then this one again, same. We're going to get a minus a fifth coming out. And then that's going to be times the cosh of x on 5. And for the stationary point, we want it to be equal to 0. So I'm going to set that equal to 0. That gives me an equation to solve. Okay, so I'm going to times that whole equation by 5. I'm also then going to divide the whole equation by cosh so that the two hyperbolic functions combine to give one tan function. So I'm going to get 3 times tan of x on 5. That's going to be minus 1 because I've times by 5, so that's gone. And then I've divided by cosh, so that's gone. And that's going to equal 0. That's then going to mean that tan of x on 5 is a third. That tells me that x on 5 is the inverse tan, or r tan, of a third. And there's a logarithmic definition for that, which is in the formula book, which is a half times the natural log of 1 plus the contents of the r tan function divided by 1 minus the contents of the r tan function. So that is going to be a half times the natural log of 4/3 over 2/3, which is 4 over 2, which is 2. So therefore x is 5/2 times the natural log of 2. Okay, there we go. There's our exact x coordinate for our stationary point. That's the only one because tan of x is only a third once. So that's the only x coordinate, which is why I changed the question to point. Okay, now we need the y coordinate, and we need it to be exact. So we're going to have to plug this in to the cosh and the sine functions here, and then you're going to use the exponential definitions to extract the exact value of y. So y, when x is 5 over 2 log 2, is going to be equal to 3 times the cosh of, and it's 5 over 2 log 2 divided by 5. Okay, so that's just going to be a half log 2. And then I've got minus sine of the same thing, so half log 2. Okay, so I'm going to use my exponential definitions for cosh and sine. So that's going to be 3 over 2 times e, and I'm going to write that as log of root 2, because it's going to be e to the half log 2, which the half comes in as a half comes in as a power, and then it's plus e, and then it's to the minus half log 2, so that's going to be the natural log of 1 over root 2. And then I've got the same thing here, except I'll get a minus in there, and it's just 1/2 out the front. So e to the log root 2. minus e to the log of 1 over root 2. Okay, so that's the exponentials. And I've written it like this so that the e's and the logs will cancel straight away, which makes my life a little bit easier. And if I boil that down, I'll end up with this whole thing as being equal to the nice number 2 root 2. Now your calculator won't give you that. You actually need to run through the algebra here. So the e's and the logs cancel, so that's just root 2. That's root 2 on 2. That's root 2, and that's root 2 on 2. And then just combine all the root 2's together. This is what comes out. So therefore the coordinate of my stationary point, okay, the exact coordinate of my stationary point is 5/2 log 2, 2 root 2. Okay, there we go. And determine its nature. Okay, so we could gradient profile. It is a continuous function. You know that cosh and sine are both continuous functions. So we can gradient profile. This is the only turning point. I'm actually going to use the second derivative. Okay, just to remind you, again, from A-level maths, the use of the second derivative. So I'm going to differentiate this again. Okay. So if dy by dx is this thing, a bit of paper, then d2y dx squared is going to equal 3/25 times cosh of x on 5 minus 1/25 times sine of x on 5. Okay, so that's the second derivative. Now if I calculate the second derivative at the point in question, so d2y by dx squared when x is 5/2 log 2, I can get my calculator up for this one, because I don't actually care what the number is, I care what the sign of that number is. So, on my calculator, I'm going to hit 2.5 log 2, so that's now stored as a and s in my calculator, and then I want 3/25 times the cosh function. Now to get the cosh function on these calculators, I'm going to need to go into option, scroll to the right to get my hyperbolic functions, F2, and there's my cosh function. Oops, I don't want the denominator there. Cosh, and that is cosh of x on 5, so that is my answer. Answer over 5. Okay, and then I need to minus a 25th, so subtract 1 over 25, and that is going to be times the sine of, again, the answer over 5. Okay, now the answer to that is 0.11. I don't care what the number is, I care that it's positive. So that means the gradient is increasing at that point, so it must be going from a negative gradient to a positive gradient. Therefore, it is a local minimum. Okay, excellent. And the final part of the question. So we've found the exact coordinates of the stationary points of this curve, and we've determined its nature, it's a minimum. Now we need to sketch the graph. Okay, so this is the only minimum, which means it has to approach infinity as x goes to negative or positive infinity. Log 2 is positive because 2 is bigger than 1, and 5/2 is obviously positive. So x is a positive number, so the turning point is going to be here, positive x. And then the y value was 2 root 2, which is positive as well. So there it is, there's my turning point. It's a minimum, so I'm going to write the coordinate underneath. So that's 5/2 log 2, 2 root 2. And we're going to end up with just a generic curve which does that. It has crossed my y-axis, so I should put on where it crosses my y-axis. So if I go back to the definition of the curve, I can plug in x is 0, and I get that y is 3. Sine of 0 is 0, and cosh of 0 is 1, so it's just the number 3. So that point there is 3. Okay. Right, that is example number 1. Example 2. Find, by differentiation, the equation of the tangent to the curve y equals x squared sine squared x plus 2 cosh squared over x plus 1 at at x equals 0. Okay, so tangent means that we need to share the same gradient. So I need to find dy by dx. So this is going to be a product rule. So this times the differential of this, I'm going to get x squared times, and then to differentiate sine squared, it's going to be a little chain rule. So that's 2 sine of x cosh of x. And then I need to do that times the differential of that, which is plus 2x times sine squared of x. So that's this term differentiated. The second term differentiated, I'm going to need to use a little quotient rule on this bit. So u is 2 cosh squared. I'm going to write that shorthand. So u primed is going to be 4 cosh sine. V is x plus 1. Therefore, v primed is 1. Okay, I'm going to carry out the product rule formula. So that is going to be plus so we're going to get vu primed, which is x plus 1 times 4 cosh sine minus 2 cosh squared, and that's all divided by v squared, which is x plus 1 squared. Okay, now that looks a bit hideous, but I'm trying to find the equation of the tangent when x is 0, so actually I don't care what the function is, I just need the value of dy by dx when x is 0. So this first term here, the x squared 2 sine x cosh x, that's going to be 0 because of the sine x and the x squared. It's also going to be 0 because of the x and the sine squared. This term here is going to be 0 because I've got a sine there. So the only one I've got that's non-zero is this one, which is going to be a minus 2. And then the denominator when x is 0 is 1 squared. So actually my gradient is negative 2. Okay. All right, so that's the gradient of my tangent. I now need to find the coordinate of the point on my tangent. So I've got the x coordinate, obviously 0. I need the y coordinate. So y, when x is 0, back to the definition up here. When x is 0, that term disappears. When x is 0, I've got 2 divided by 0 plus 1. So I get 2 over 1, which is 2. So therefore it goes through the point 0, 2. Okay, so it's got a gradient of minus 2, and it goes through the point 0, 2, which is actually the y-intercept. So I can straight away state that y must equal minus 2x plus 2, or if you like, 2 into 1 minus x. And that's the equation of my tangent. Okay, so that is a very simple tangent example. Okay, and one final example for this video before we finish up here is an integration question. So we are going to find the integral from 0 to log 2 of x times sine x dx. I'm going to leave our answer in this form where a, b and c are all integers. So we've got an integer times log 2 plus an integer on the numerator and some other integer in the denominator. Okay, so if this was a sine function, you should immediately be thinking I need integration by parts to integrate this. So that's exactly what I'm going to do. Okay, so integration by parts. So I'm going to call this I, so I can just keep referring to it. U is going to be x, so that u primed is the number 1. I'll get rid of that polynomial at the front. V primed then is sine of x, which means that v is the cosine of x. Okay. Now I can plug those into my integration by parts formula, which is uv, so x times the cosh of x, and it's a definite integral, so to be mathematically correct in my notation, I should put that in square brackets and put my limits on there, so 0 to log 2. Subtract the integral from 0 to log 2, again the limits carry through, of vu primed, which is the cosh of x dx, and that is just going to be the sine of x. So I is going to be x times the cosh of x minus the sine of x from 0 to the natural log of 2. Excellent. All right, now I'm going to substitute in my upper limit and my lower limit in here. So that's going to be log 2 times the cosh of log 2 minus the sine of log 2. And then plug my lower limit in, I get minus 0 times 1. And then I get minus minus 0. Okay, so those two terms disappear. So I just need to think about what cosh and sine of log 2 are. So I can either use my exponential definition, or because they are logs, actually they do come out to be nice fractions here. So let's try that. So cosh of the natural log of 2 is 5 quarters. And then I can do the same thing with my sine. So I get sine of log 2 is 3 quarters. And it wants it written as a single fraction. So I see my 4's are a common denominator. So I'm going to write that as 5 log 2, subtract 3, all divided by 4. And we can see that this is now of the form that the question wanted. So I'm going to leave my answer like that. What I will do, however, is just check my answer. So again, back to the GDC, I'm able to just check it by using some calculus. So if I integrate the original function, which was x times the sine, let's go back into my options now, hyperbolics and a sine of x, and that's between 0 and the natural log of 2. Okay, so that's got my my question in there, and I'm going to subtract the answer I got. So the calculator won't give this as an answer because it's got a log in it. But if I subtract this number, then if this number is right, then this calculator will give me the number 0. So I get 5 log 2, subtract 3, divided by 4. And that is 0, so that allows me to confirm that this is right, and I'm able to move on from this question, knowing I've got full marks for it. Okay, so those are the 3 examples I wanted to cover. If you stuck with me this long, then very well done. I hope you found that useful. Just a couple of closing remarks before we finish up this video. As I said at the beginning, these concepts that I've just taught are added to everything you already know from differentiation. So I've got a little list here. It's not exhaustive, but all of this can be used in conjunction with finding the gradient at a point, increasing, decreasing functions, stationary points, finding tangents and normals. We did an example on that. Classifying stationary points using the second derivative, concave and convex functions, looking at the sign of the second derivative. You might have implicit differentiation coming in, or Maclaurin series, which will come in the next calculus section. We might have that on some hyperbolic functions. So all of this can be used in conjunction with hyperbolics. And then with the integration, again, you've got all of this stuff that you've already learnt with integration, and this is now just an extra bit to add to your toolbox. So reversion differentiation, you've got finding areas below curves, below axes, between curves. Just be careful when curves cross. Integration by substitution, integration by parts. And then we've got mean value theorem, which will come in the next section. That could come up in with hyperbolic functions. Volumes of revolution, so you've met those. Okay, just whack it in the formula and integrate. Polar coordinates, I don't think they will have a polar definition using hyperbolic functions. It's usually trig functions for that. But, I mean, the maths is there. It wouldn't be off syllabus to ask a question, but you wouldn't really use hyperbolics with polar coordinates. So yeah, just don't forget that all of this can be combined into kind of big questions. All right, thanks so much for watching, and check out other videos for help with your further maths learning.